So welcome back this evenings. This is MP Live Lessons once again, and we're going through GCSE Maths Paper 3 for both tiers in AQA. So based off the advanced information, I've seen that both tiers will have factors and multiples. So we first need to know the basics. So a factor is a number that divides exactly into a larger number without leaving a remainder. For example, 6 is a factor of 48. You may note that prime factors are just the factors that are prime numbers. You may need to decompose them, which you'll need to see in a bit. You'll also need to know about multiples, which are basically the times tables of a number. For example, 49 is a multiple of 7. As a result, you'll need to also know the LCM and HCF. So the LCM is the lowest common multiple, and the HCF is the highest common factor. And you'll be asked to find these between two or more numbers. For simpler questions, you'll need to write each factor or multiple out, and then find the highest one or the lowest one in common. For example, find the lowest common multiple and highest common factor of 15 and 9. So if we do the multiples, we have for 9 and then 15. So we have 9, 18, 27, 36, 45, 54, and so on. Whereas 15s, we have 15, 30, 45. And we can already see we've found the lowest common multiple, so the first multiple that appears in each list that are in both. Whereas highest common factors for 9, 1 is always a factor. Does 2 divide exactly? No. 3 does. 4 does not. 5 doesn't. 6 doesn't. 7 doesn't. 8 doesn't. And lastly, 9. And we are going to look at the factors of 15. 1 is also a factor, along with 3, 5, then 15. So that means we can see the highest common factor, the one found in both lists, is 3. So this can be applied for, let's say, buying batches of something, let's say packs of plates for a number of people. Such as how many packs of plates are needed, let's say if there's 20 each to supply a crowd of 95, perhaps. Or it could be perhaps to match the number of plates and let's say number of straws. So that's how it can be applied. Now, still for both tiers, you'll need to know how to split a number into its prime factors. This is because you need to answer harder questions, so those with larger numbers. So you'd use normally a tree and then break the number down into 2 factors at a time until all factors at the bottom are all prime numbers. Now, if a prime number appears more than once, you need to collect them together and use the laws of indices. So that's why you can see it written in index form. For example, if I write 212 as a product of its prime factors and give them an index form. The little trick is, you could do this, if you have a Casio calculator, the expensive ones, you can type in your number, press equals, and then press shift, and then find the button with the yellow fact near it. And it'll split the number into its prime factors, or products of its prime factors. So if I start with 212, I could break this down into 2 and 106. So just notice that these two numbers will multiply back up to the number above it, that's its paired. I could then try 2 again. That gets 53. I'm sure 53 doesn't go or doesn't have any other factors because it's a prime number, it only has one in itself. So at the end, 53 is a prime number, so it's 2 and 2 here. So there's 2 times 2 times 53. So we can group these 2's together. So there's 2 being multiplied twice by itself, so that would be 2 squared times 53. Now, to apply this, we'll use an example. So for example, find the lowest common multiple and highest common factor of 80 and 105. So we'll first draw the factor trees for each. So to find the lowest common multiple, what we'll do is we'll line each of these up. And by aligning them, I mean putting the same like prime numbers in between. For example, we'll put 2 to the 4 in one column times a blank, which is for 3. Then we have times 5 and times 7. So we just align all the prime numbers together like this. Then what we do is we take the highest power from each. For example, if there's no power, it's just a 1, like this. So that means your lowest common multiple is 2 to the 4, that's your highest one, times 3 to the 1. That's your like highest one as well. Your highest one is 5 to the 1 here, is the same, and then 7 to the 1. This gets us 1680. And lastly, for the highest common factor, you'll need to write them out again, leaving the gaps where you need to. This time you take the highest power that goes into like both numbers. As in, for example, there's no common power for the 2's here, because 105 does not have 2 as its any of its prime factors. Same with 80 and 3. 3 is not found in the prime factor tree, but 5 is. So the highest common power that goes into both, or found in both, is just 1. So that actually is our highest common factor. Next, you need to learn about error intervals. So let's say a field's length is said to be 80 meters to the nearest 1 meter. So what are the smallest and largest lengths of the field before it was rounded? So these are lower and upper bounds. Realistically, it could be anywhere between the lower, which is 75 meters, actually 79.5 meters, which is it including, for the upper bound, it would be something like 80.4, like 999 and so on, recurring. So really we just write this as 80.5 meters as the upper bound, so it does not include it. So if you write this as an inequality, so let's say we'll call the length as an L. So the upper bound goes on the right, so that'll be 80.5. Your lower bound goes on the left, 79.5. write your units on, put your L in the middle. Now it will include the lower bound, so it needs to be equal to as well. So the length is greater than or equal to 79.5, and it doesn't include the upper bound, so it just needs to be this. It it can go right up to 80.5, but not including it. So overall, the upper and lower bounds are like half a unit, like each side of the rounded value. So each unit, so like how much it was rounded by, was 1 meter. So plus or minus like half a meter. So when we work with error intervals, for example, when two values are rounded, you could then be asked to add them or multiply them or subtract them and divide them and find again the lowest or highest possible value. And some common examples can be filling bottles with some liquid. For example, if we had a set volume of water to like the nearest 10 liters, and then we filled bottles up that had, let's say, half a liter to the nearest 0.1 liters, how many bottles could we fill up, the minimum or the maximum? You could also have error intervals for area and just the largest or smallest value for an expression. So for example, when we're adding or multiplying, so let's say we have two numbers, A and B. A is said to be 2.5 to 1 decimal place, and B is 8 to the nearest whole. So we find the lowest and highest value for A plus B and A times B. So first we've got to write the error interval for each. So 1 decimal place is just 0.1. So if we half that, it's 0.05. So that'll be over or under. So A would be between 2.45 and 2.55. And nearest whole is just 1, so that'll be half above or half below. So B is between 7.5 and 8.5. So to find the lowest and highest value for either of these, to find the lowest, you have the lowest possible value for A and the lowest possible value for B. So for example, A plus B would have a minimum value of 2.45 plus 7.5, which is 9.95. So if I write the error intervals again, the opposite is for the highest possible value. You'll have the highest possible value for A and the lowest possible value for B. And the highest for both, actually. Now I think I actually erased stuff, right? If I write this again, So for the highest values, you'll have the highest value for A and the highest value of B. So for example, if you add them together, you'd have the highest value of A, which is 2.55, and then you add on the highest value for B, 8.5, and you get 11.05. Something similar happens with multiplying. To get the largest possible value when you multiply the two numbers, you'll have the highest value for A and multiply it with the highest value for B from your bounds. So applying this, for example, let's say a garden measures 50 meters by 5.5 meters, and they're rounded to this degree of accuracy. So to the nearest meter for the first one, to the nearest 0.1 meters for the second one. So if we calculate the error intervals, so we'll call this 50 meters the length and the 5.5 meters the width. So the length could have been anywhere from 14.5 meters to 15.5 meters, but not including it, because we take half units, which is half a meter, and we add and subtract it from the rounded value. We'll do something similar for the width. So half a unit will be 0.05. So we add this or subtract this. So the lowest or shortest length possible was 5.45. And then the largest possible length was 5.55. So calculate the smallest and largest possible area and perimeter. So perimeter is you add up all the sides. So if I draw a little diagram on the right, so this would be your 15 meters, roughly to 1 meter, and then the width would be 5.5 meters to 0.1 meters. So the perimeter is this side, this side, this side, and this side. Now you know all the opposite lengths are equal, so you have two lots of the length and two lots of the width. So for the smallest, you'll have two lots of the smallest value for the length, which is two lots of 14.5 plus two lots of the smallest width, which is 5.45, which means the smallest possible perimeter is 39.9 meters. And the largest possible perimeter is your largest possible value for L, 15.5, plus your largest possible value for the width, which is 42.1 meters. And if the area, it's something similar. So the area is the length times the width. So the smallest is your smallest possible value for L times your largest, smallest possible value for W, which gets us 79.025 square meters. If we do the largest, 15.5 times 5.55, because those are the largest possible values for the length and widths, which gets 86.025 square meters. Now we'll do something similar with subtracting or dividing with error intervals. So let's say we have two numbers again, a and b. A is 30 to the nearest 10, and b is 0.8 to the nearest 0.1. So if you do our intervals again, so the half a unit above or below would for A is just 5, whereas for B, you add or subtract 0.05. So that means the smallest possible value for A is 25, the largest is 35. The smallest possible value for B is 0.75, and the largest possible value is 0.85. Now, to find the lowest and highest possible value for A take B, or A divided by B, it's similar again, but different compared to adding and multiplying. So to find the lowest this time, so you'll start off with the lowest possible value for A, and then you take away the largest possible value for B. So for example, when you're dividing, since you're dividing by a larger number, it will make the value much smaller. And if you're subtracting, you'll be subtracting by a larger number, which will get you a lower value. Whereas the highest, it's your highest value for A, and then your lowest value for B. So for example, A minus B. So the lowest possible value would be 25 minus the highest possible value for B, which is 0.85, 24.15. Overall, the largest possible value for A minus B would be the largest value for A minus the smallest possible value for B. This gets 34.25. And we do something similar for A divided by B. So for the highest possible value, you'll have your highest A and your lowest B, which is 35 divided by 0.75, which is 46.6 recurring. Then if you do the opposite, the lowest value of A divided by B, so you'll start with the smallest value for A divided by your largest value for B. Which gets 29.41, which even then is ironically rounded. So let's say we've got another practice question. So we've got a business catering for an event, which is an estimated 12,000 people to the nearest 100. So they can cater for the event using trucks, which can cater up to 250 to the nearest 10. So calculate the error interval, so the minimum and the maximum number of trucks needed to cater for the event. So the lowest number of trucks needed is if you got the smallest crowd possible. And you divide this by the largest catering capacity, or the largest number of people served by each truck. So in that case, that would be the smallest crowd, since it's rounded to the nearest 100, that's plus or minus 50. That would be 12,050. Wait, 11,950. We divide this by the largest number of people the trucks could serve, so that's 250 to the nearest 10. So if we take half of that, it'll still be plus or minus 5. So we can cater up to 255 people. So that means that needs 46.86 trucks, which doesn't make sense, but yet we'll see for the highest interval. So for the largest, it's the opposite, so we have the largest crowds possible, divided by, like, let's say the trucks on a bad day won't serve as many, so there'll be the smallest number of people served. So that'll be 12,050 divided by 245, because 245 is the minimum number of people the trucks would serve if it's 250 rounded to the nearest 10. So at the maximum, you'll need 49.18 trucks. So for both of these, it makes sense to round up to the nearest whole number, regardless of what it is. So you'll need at least 47 trucks to just under 50. Because if you rounded down, you'd be using fewer trucks and they won't be able to accommodate all those people. Now, next for higher tier is recurring decimals to fractions. So a trick here for the easy ones is, let's say, converting 5/9 to a decimal. So we just have to use the bus stop method, 5 on the inside, 9 on the outside, divide, just add loads of zeros here and you'll immediately see a pattern. You'll see the 5 will just keep repeating forever. So this is what's being repeated. So 5/9 is 0.5 recurring. So this means this 5 here is the recurring bit. It will keep repeating infinitely if you carried on with division. Now, if you're converting recurring decimals back to a fraction, and if you have, let's say, something like this, 0.424242, which I'll write as 0.40 recurring like this. So basically, if the recurring bit immediately starts, what you do is to find a denominator. It'll be like 999 or 999, so it depends on how many digits are in this recurring bit. So since there are 2 digits in the recurring bit, we need 2 nines, or 99. So our denominator is 99, and we just put this on top, this recurring bit on top. So that's 42/99, and this can be simplified actually. If you divide both the top and the bottom by 3, you eventually get 14 divided by 33 as a fraction. That's simplified. Now you might have slightly harder ones where, let's say, in this case, the recurring decimal does not immediately start after the decimal point. This would be written as 0.812, so the dots are over 1, 2. So this section here keeps repeating. To make things easier, we want this recurring bit just to be right after the decimal place. So we multiply, let's say we let x equal our recurring decimal, Now, if we first multiply this recurring decimal by 10, so x times 10, the decimal point will shift one place to the right to make everything 10 times larger. So you have 8.12. So then this 1, 2 recurs. Now, what we want is one lot of this recurring bit to get to the other side of the decimal point. So we shift the decimal point 2 times to the right again, so that will be 10x times 100x. This eventually gets 812.12 recurring because this 1, 2 will keep going on forever. And if we take both sides, what happens is these two recurring bits will just cancel out nicely. And you're left with 804 on the right for a value. And on the left, 1000 take away 10. That would be 990x. Then you divide both sides by 990 to get x on its own. You're left with 804 divided by 990. This would be simplified to 134 over 165 eventually. Now next is ordering fractions. So let's say we've got 4 fractions here, and first we need to make sure that all fractions have the common denominator. So we do this by multiplying each fraction until they have the same denominator. For example, in this case, an appropriate denominator you could have could be 126. So let's say common denominator is 126, which actually works for this, but I'm giving a hard example. If I write out the fractions again, and I put all the common denominators, we just need to figure out what each will be multiplied by, just because to make equivalent fractions, you need to multiply the top and the bottom by the same number. To get from 6 to 126, we have to multiply by 21. So this gives us the equivalent fraction of 105 over 126. To get from 7 to 126, we have to multiply by 18. So this gives us the equivalent fraction of 72 in the top divided by 126. To get from 3 to 126, you multiply by 42, which gets us the equivalent fraction of 84 over 126. To get from 9 to 126, we multiply by 14, which gets us the equivalent fraction of 70 over 126. So now that we've got all the fractions in having like a common denominator, you can easily compare them now based on just the numerator, because they're like split up into the same number of slices, if you like. So you can compare them easily. For example, this will be the smallest, then this one, and this one. So I've got them 1 as the smallest, and the 4 is the largest. Now I put them into order, but write them in their original format. So what we were asked in the question. So the smallest one is 70 over 126, which was in the question written as 5 over 9. Next was 72 over 126, written as 4/7. Then 84 over 126, which was 2/3. Lastly, 105 over 126, which was 5 over 6. So in their original like fractions. Now next is for both tiers, you'll need to know the general formula for speed. So average speed is distance divided by time. So usually you may be given unfamiliar units. So to find the units for speed, so your distance is usually measured in something here, and time is often measured in either seconds, hours, minutes maybe. And then distance can be measured in anything from like centimeters, meters, and so on. So when you divide the distance divided by time, you have the unit for distance and you divide it by the unit for time. So your average speed will look like the unit for distance divided by the unit for time. For example, a car will travel 76 kilometers in 90 minutes. So calculate that car's average speed in kilometers per hour. So we pay attention here. So kilometers is our unit for distance, and hours is our unit for time. But you notice it's not the same. There are 60 minutes in an hour. So that means if we go from minutes to hours, we divide by 60. So 90 minutes is 1.5 hours, so 1.5. So overall, the average speed is 76 kilometers in 1.5 hours. So your distance, 76 kilometers divided by the time, which is 1.5 hours or 1.5. This gets us an answer of 50.7 kilometers an hour per hour. That'll be to 1 decimal place. Now, what's also on both tiers is sharing in ratios. So my method is to do it by parts. So for example, in the ratio 4:9, how many parts are shared all together? It's easy. So we just add these up. 13 parts are shared. So one person gets 4 of the 13 parts and the other gets 9 of the 13 parts. And one example of these sharing questions could be for foundation to share, let's say, some money in the ratio. So we have £40,000 in the ratio 14:11. So we first find out the number of total parts. That's 25. So we have 14:11. That's going to be 25 parts. So you want to scale this up in a way so that now instead £40,000 is shared. So to get from 25 to 40,000, you multiply by 1,600. In other words, there is 1,600 per part that is shared. So basically what you can do now is multiply each bit in the ratio by 1,600 and you'll see what each person will get. So 14 times 1,600 gets you 22,400, and then the other person will get 11 times the 1,600, 17,600. Now for higher tier, they might involve use some algebra as well. So let's say we've got 800 liters of fuel shared into 3 tanks, A, B, and C. So all the fuel is shared so that tank B gets n liters of fuel, tank A gets 60 more liters than tank B, and then tank C gets half as much fuel as tank B. So we know already that tank B gets n liters of fuel. Now tank A gets 60 liters more than tank B, so tank B gets n liters, so tank A gets 60 more than that, so that will be n plus 60. And then tank C gets half as much fuel as tank B. So tank B gets n liters of fuel, tank C gets half as many, so there'll be n divided by 2. And we know that 800 liters is shared in total. So we do a similar method again, so we add these little parts up, even though it's not really obvious. So we have tank A, n plus 60, tank B, n, and then tank C, and we set that equal to the total of 800 liters. Now if we mess around with the equation, we get 2.5 n plus 60 is 800, so 2.5 n equals 740, therefore n is 740 divided by 2.5, which gets 296. So that means, so for each tank, so if you return to the question, we want to find out how much fuel is in each. So tank B gets n liters. We already know n is 296. Tank A gets 60 more liters than tank B. So 296 plus 60. So that's 356. And then tank C gets half as much as tank B. So 296 divided by 2, which is 148 liters. Now, for foundation, you'll need to know about fractions to percentages. So percent can be broken down into percent, which means per 100 parts, which you should know already. Now, to convert a fraction to a percentage, you can either, for example, find an equivalent fraction with a denominator of, let's say, 100, and this works well for some fractions, like 8 over 25. You can make an equivalent fraction with the denominator of 100. You get from 25 to 100, we multiply by 4. So therefore, we multiply the top by 4 and get 32 over 100. So that means 32 parts per 100, so 32%. You may get harder ones, so you have to multiply the fraction by 100. So first you have to put the fraction into your calculator. So you press the fraction button, put 22 in the top and 45 on the bottom, and you multiply that by 100, and this instantly gets you your percentage. In this case, that would be 48.5%. 0.8 recurring percent. I'm just writing what's on the display of my calculator. And obviously, since this is paper 3, you'll be allowed to use a calculator. Now for both tiers, it may be helpful to know about the percentage increase, and I'll introduce something called the multiplier. So let's say we want to increase the amount of £350 by 12%. So we first want to find the multiplier. So that will instantly increase £350 by 12%. And just remember that 100% is the original amount. So in this case, the multiplier is 1 plus your percentage. And remember, if it's an increase or decrease, if it's an increase, it's positive, so positive 12 over 100. And this gets you the multiplier of 1.12. So if we immediately multiply 1.12 times £350, this gets us £392. Now this method is actually much faster than finding the 12% and then adding it on. But even then, if that method works for you, just do it. It will still get you the same number of marks. Now, however, these multipliers could be useful for compound interest, which is mainly come up in higher tier. So let's say, in a petri dish, there are estimated to be, let's say, 400 bacteria, and the population of bacteria increase by 11% every hour. How much bacteria will there be in the dish after 24 hours? So we first have our multiplier, which would be 1 plus your percentage divided by 100, so this is overall 1.11. That's your multiplier. Then we use the formula for compound interest, so we have our initial amount. So that's 400 bacteria multiplied by the multiplier in brackets. And this is to the power of time, so time is in how many times it's repeated. In this case, it's every hour, and then that's for a total of 24 hours. So that'll be to the power of 24. Put this into your calculator. You get a very large amount, well, a lot larger, which is 4,896. So that's the nearest one. Now we'll move on to some algebra now. So there's some number machines or functions, which we may come to later. So a function will have an input, do something with it, and then output another number. So let's say we have the function where we input something, it adds 5 to it, then it gets squared. So if I draw this like the number of machines you'd have seen in primary, they have your arrows, you have like little machines like +5, and they'll be seen a bit like little cameras, like this. It'll just spurt out whatever is in here, then it will be squared. And that gets you your output. And you have your input at the start. So for example, if the input is 3, so we put input 3 here, we add 5, that becomes 8, that gets squared, you get 64. So your output, 64. Now we'll try input 0 into it. So input 0, we first add 5, then we square it. So output 25. Now, For higher tier, what if we input x? So we first input x. If we add 5 to it, it just becomes x plus 5. If we square this, we have to write in brackets x plus 5 squared. So our output is x plus 5 squared. If you want to expand this, it's acceptable as well. You'll get x squared plus 5x plus 5x plus 25 if you did FOIL method. And you'll eventually get to x squared plus 10x plus 25. Now, let's say this function is labeled f. Now, f of x would just be this right here. So you'll have your function all just labeled f. It'll take in an input and spew out an output by adding 5, then squaring it. So basically this x here tells us whenever you, like let's say input a number, you'll substitute that in wherever you see x in this function or equation. For example, if we wanted to input 3, we'd just write f of 3. And we'd put 3 in wherever we see x. So that'll be 3 plus 5 squared, which is 8 squared, which is 64. So it works in the same way, basically. Now, continuing on functions, just for higher tier, we'll need to know about composite functions. So let's say we have two functions, f and g. F of x is 3x plus 2, and g of x is x plus 2 all squared. Now, if we write both of them as number machines, we'll have our function f, so input will then first multiply by 3. So we see what's happening to x. So it's first multiplied by 3, since there's nothing in between the 3 and the x. Then we feed that into something that will add 2 to it. And that gives us our output. That's f. Now for g, we'll have our input. We'll first add 2 to it. Then we'll square it. That's our output. Now, let's say we'll calculate the value of f of 3. So f of 3, to help with the number machine, we'll first multiply it by 3. So 3 times 3, then add 2, which gets us 9 plus 2, which is 11. Now we put this result into g. So that's g of 11, which is, we add 2 first, so 11 plus 2 all squared, that'll be 13 squared, which is 169. So what we've just actually done is calculated g of f of 3. So we basically, it's best if we put brackets around it like this. So we first input 3 into the function of f, and then, if I put this in a green pen, we put this result into the function of g. So it goes through one machine and into another. This is what a composite function is. So we have another example here. And let's say we've got fg2 and then gfx. So it's better to probably put brackets around what's inside. So we first need to figure out g of 2, which is 2 plus 2 all squared, 4 squared, which is 16. Now we put this into f. So that is 3 times 16 plus 2, which gets us 50. Now if we draw brackets around f of x here, what we can see is f of x, so that is 3x plus 2 inserted into g. So we can basically rewrite this. So we have g in the brackets, the function of f of x, which is this, 3x plus 2. Now, wherever we see x, we write what's in here, in the brackets. So we have 3x plus 2, that's where the x went, then plus 2, all squared. This gets us 3x plus 4 squared. Now if you want to simplify it, you'll get 9x squared plus 24x plus 16. Now, as an extension, try and solve this. So we've already got g of f of x, so that's 9x squared plus 24x plus 16. So if you find what f g of x is, so we put in g of x, the function of g of x, into f, so the function f. So wherever we see x here, we put this in. So this becomes 3 lots of the bracket, whatever's in the bracket. Then we add 2. Three x squared plus 12x plus 14. So that's this fgx. So we set this equal here. Now we put everything onto one side, and then we'll use the quadratic formula. So we take 3x squared from both sides, so we get 6x squared. So that cancels this out. To get rid of this, we take away 12x on both sides. And to get rid of this, you'll take away 14 from both sides. So you're left with blank on the right, and then just plus 2 on the left, and that's equal to 0. Now if we use the quadratic formula, what we'll get is root 6, which is, if we divide everything by 4, so that means your two solutions are x equals, so we have our first one, so we add on the root of 6, so minus 3 plus the square root of 6 divided by 3. This is minus 0.18. Then we do the other solution, minus 3 minus the root of 6 divided by 3 altogether, so this gets us minus 1.82. So these are given to 2 decimal places. Now I'd like someone to check if I'm right as well with this, and then just comment down below. Now we move on to some more real algebra, so everyone needs to know how to simplify expressions. So the basic rules are, you can only collect like terms together. For example, if we try to simplify this, we can collect these x squared terms together, and remember, if there's nothing before the letters, it's just a 1. This becomes 2x squared. These x terms can be collected together. And remember, pay attention to this minus here. So we have positive 5, then minus 2, so just plus 3x. And then we have positive 1 here as a number, and then negative 5 here. That's minus 4. And then next, for basic simplifying, if you're multiplying or dividing, don't forget to follow the laws of indices. For example, 2a squared times a times 5a. So we first deal with all our normal numbers. So that's like our 2 and our 5. So that 2 times 5 is 10. Then we have each of our a's together. So it'll be a squared times a times a. Just remember, if there's no power, it's the power of 1. So when we multiply powers like this or indices, we add them together. So you just get to the power of 4 at the end. So a to the power of 4. So 10a to the power of 4. Next example is this. So we start off with our normal numbers. 8 times 4, 12. And we have our c times our d. So just cd, because they're different letters, they can't combine together. And lastly, this here. So this power of 3 will apply to everything inside it. It's almost like expanding a bracket. So this will apply to the normal 2. This will also apply to that n cubed thing. So if we have a 2 to the power of 3, and then brackets n to the power of 3, that to the power of 3 as well. So 2 to the power of 3 is 2 times 2 times 2, which is 8. Times, when we have a power raised to another like this, we multiply the powers, so n to the 9. We don't need this multiplying sign, so that's just 8n to the power of 9, like this. Now with expanding brackets, which I briefly mentioned, to expand means to multiply out some brackets, such as this. So each bit on the outside is multiplied with everything on the inside. So we have 2x times 4x, and then we have 2x times positive 3xy. So remember from the previous slide, you remember how to multiply each of these terms. So we first deal with our normal numbers. So 2 times 4 becomes our 8, and the two x's multiply together, x times x, become x squared. And then we have on the right for the second term 2x and 3xy, so we start with our normal numbers. 2 times positive 3 gets us positive 6, and then we do the letters separately. So we start with x, so x times x, that's x squared, and the y is just on its own, so like this. Now, however, a common mistake that many people make are with negatives. So for example, this. So pay attention to this negative 2 here. So this gets multiplied within everything along with the y as well. So our first term is negative 2y times 3x, and the other term is negative 2y times negative 2. So first we have our normal numbers for our first term, negative 2 and 3. That becomes negative 6. And the letters are different, so you just combine them together and put them in alphabetical order, preferably. So ideally minus 6x, y. Now for the second term, we have negative 2 and negative 2. 2 negative makes a positive, so we just have 4 and the y on its own. So overall that's 6, negative 6xy plus 4y. Now, you'll need to know how to expand some double brackets as well. So method 1 is FOIL. So this is best for two brackets with two terms each. So FOIL stands for the first, then the outer, then the inner, then the last. The second method is the grid method, which is better for various numbers of terms. And I've already tested each method actually in the previous video. And I'll just do one example of each, which is with this example here I'll choose. So on the left I'll do FOIL. So we have 2x minus 3 and 3x plus 4. So we do our first few terms, so 2x times 3x. So our first term, the f, is 6x squared. Now we do our outer one, so this, and then so that will be the outer ones here. So the 2x and the plus 4. Multiply them together, you get positive 8x. And then the inside terms, so that's the negative 3 and 3x, you get minus 9x. And then the last terms, the minus 3 and plus 4, that's minus 12. So if you tidy this up, you can see that these two terms can be collected together. So that's 6x squared minus x minus 12. Now for the grid, you'll draw each term out separately. So the x term will just be 2x on the top, and then the minus 3, just the negative 3 here. So each bracket goes on the either the top or on the side. This 3x would go here. This plus 4 just goes here. So what you do is you kind of line up here. For example, the 2x and the 4 will multiply together and form 8x, and you put this here. So you almost line up with each, like a coordinate. So at the end you get 6x squared. And nicely that these two terms here on the diagonal can be collected, and you get the same answer. Now, for higher tier, definitely, you'll need to expand 3 or more brackets like this. You can still use FOIL all the grids, but you have to expand 2 of the brackets first. For example, I'll expand these brackets first, and you'll eventually get m squared minus 2m minus 15. Then we multiply all this with this bracket here. So we'll put this into another bracket. And we'll just do a grid. So we have our 6m cubed minus 6m squared minus, that's going to confuse a bit, 45m plus 60 here plus 8m, and then minus 4m squared. And then we see on the diagonal that these terms will collect together. So in the end we get 6m cubed minus 10m squared minus 37m plus 60. Now, for both tiers again, you'll need to factorize and do this with single brackets. So you have 4 steps here. So you find the highest common factor for each of the numbers, and then the letters as well. And then divide each term by the numbers and letters, and then you check if they're fully factorized, if you can do this whole thing again. So for example, if we factorize this, only the number will go into both terms. because the letters aren't found in all the terms. So the highest common factor for 10 and 12 is just 2. We divide each term by 2, so 10x divided by 2 is 5x. And then 12 divided by 2 is just positive 6. That's it for factorizing, because you can't factorize anymore. Next is 4x squared plus 6x. So our number, I can go into both, the highest common factor for the number is just 2 still. Now we've got letters as well, and we get the lowest power for each. So just x can go into both. So 4x squared divided by 2x, so 4 divided by 2 is just 2. And then x squared divided by x is just x. And then we have 6x divided by 2x, so 6 divided by 2 is 3. And then x divided by x is just 1. So we leave it as it is, and that's our fully factorized bracket. And lastly, another example. Now, it looks more complicated, but we'll go through the letters A, then B, then C. So you can only take them out if they're found in all of the each term. So 4 can go into all of these terms. So 12 divided by 4 is like 3. 8 divided by 4 is 2. 4 divided by 4 is just 1. So 4 is our numeric, or the number, highest common factor. Then we look at all the A's. So we have an A here, an A here, and an A here. So the highest, the highest power of A that will go into each of these is just 1. So A. Not all the terms have a B, not all the terms have a C, so that's our factor. So 12AB divided by 4A, so 12 divided by 4 is 3. A divided by A is just nothing. So 1 actually, but just we ignore it. It cancels out. Then B, it's not divided by any B, so that's just B here. 8 divided by 4, so negative 8 divided by 4 is negative 2. A divided by A is just 1. There's nothing to divide C by, so just C here. And then 4 divided by 4 is 1, so we don't write anything yet. And A squared divided by A is just A. And the B isn't divided by anything, so just the B is left as it is. Now for higher tier, you'll need to know how to factorize quadratics. So the main method you'll be taught is to list out the factors or numbers that multiply to make C, and then find the combination that adds to make B. For example, x squared plus 10x plus 24. Eventually you'll find that the two factors of 6, positive 6 and positive 4 multiply to get positive 24 and add to get positive 10. So our two brackets are x plus 6 and x plus 4. Another example can be this. So we want two numbers that multiply to 16 and add to negative 8. Now, as a little hint, if C is positive, so the last number is positive, you can either have two positives or two negatives. Now, it's likely two negatives because we want the factors to add up together to make a negative number. If you found it, great, because it's negative 4 and negative 4. So negative 4 times negative 4, the two negatives cancel out and become positive. So that's positive 16. And then if you add them together, it's negative 8. So your two brackets are x minus 4, x minus 4. You could also write this, since they are the same brackets, x minus 4 all squared. And the last example for this is a difference of two squares. So what we do is we imagine there's like a 0 in front of an x here. Like plus 0x minus 25. And usually with a difference of two squares, what we do is we square root this here, and then we add or take away in the brackets, whatever that was. So we square root 25, which is 5, so that will be x plus 5 and x minus 5. Now you might get some harder ones. For example, you'll have a number before the x squared term. And we need to edit the method, so we first list the factors that make up a times c, or that will multiply to form a times c. And then we pick again the combination that adds up to make b. But this time we'll split b with the factors, and then factorize each half and put them together. So an example is this. So AC is 2 times negative 15. That is negative 30. So you want two numbers that multiply together to get negative 30. Then B is negative 7. You want two numbers that add to make negative 7. Eventually you'll find that it is negative 10 and positive 3. So if we split x like this, so we'll have minus 10x, then plus 3x. So we write it out as 2x squared minus 10x plus 3x minus 15. And you factorize, you split them down the middle and factorize each half. Then you'll put these two brackets are the same, so that becomes one of them. And you combine these two terms to get the second bracket. Now, a second example is this here. So you want two numbers that multiply to make AC. So AC is the 6 here times the 6, that's 36. You want two numbers that multiply to make 36. And you want them to add to B, which is 13. This is 12, positive 12, and positive 3. So we split them. So we have 6x squared plus 12x plus 3x plus 6. So we split down the middle again and we factorize each half. Nicely again, the two brackets are the same on each half, so that becomes one of the brackets. And we combine the other two terms outside the brackets to get the next one. This should really be a 15 as well, I think. Oh wait, hang on. It's actually plus positive 4 and positive 9. Sorry. Split again, factorize each half. So we have the same bracket in each half. That becomes one of them. In the second bracket, the remaining terms here. Next is completing the square, which was in the last paper as well. So let's say we expand this, and what we notice is, so this is, let's call this a number like b. So this is b squared, and this happens to be 2 lots of b. So completing the square involves putting some like quadratic expression into x plus a number all in brackets, and then he add or subtracts a number at the end. So we need to, for example, manipulate this expression to complete the square. So what we do is we half the middle number. That goes in our brackets, all squared. And what we do is to kind of correct the bracket, because what we had was this b squared at the end. We have to take it away, so take away 3 squared, and then add the 2 at the end. This means we get in the end x plus 3 squared minus 7. And if you expand the brackets out, you will originally return back to this. Now, for turning points, this is on both tiers, so the easiest way you can find a turning point is if they give you a graph. This is very generous. This is the easiest way. So for example, you have, let's say, a quadratic graph like this. The turning point is literally just here at its lowest point. Sometimes it could be the other way around. So the turning point can either be a maximum, or like a peak, or a minimum point. Before it just turns around again and goes the opposite direction it came from. Now, mainly for higher tier, you'll need to find the turning points of a quadratic equation based off its equation. So let's say you'll first have this equation here, and what you'll have to do is complete the square. If we do this, we get awkwardly is this. Now, what we do is we substitute negative a into x. So what it basically does, it makes this bracket equal 0. So that x is equal to negative 5 over 2. It makes the bracket equal 0. That means you're just left with this here at the end. So that means y is minus 8.25. So your turning point is minus 5 over 2 minus 8.25. Now, roots on a graph are something else you might need to be like identifying, let's say from an equation as well. So a root on the graph is where it crosses the x-axis. So the values of x where this happens are called the roots. So you can find the roots by solving an equation by like substituting y equals 0. Now, a little notice, for example, for quadratic equations, if I have a little sketch here, this is the x-axis, this is the y-axis. Let's say it comes down like this. Now, this is one root here, this is another root. So if I just sketch this again, what you notice is, if you find the average between the roots, if you add them together and divide by 2, is that they form a little line of symmetry, and this is the x-coordinate of the turning point. And this can be found by adding the roots together and dividing by 2. Because the quadratic graph shape is like symmetrical down the center where the turning point is. Now, likewise, you'll have to sketch a few graphs and you'll need to look for a few things we talked about, such as intercepts. That's where it crosses an axis, like the roots will cross the x-axis. You'll need to probably look for turning points as well. You could just even be given them and you'll need to label them. Now, for linear graphs, you'll have to look something like this. That was a bad drawing. Just a straight line. And don't forget, this is your y-intercept. That's at x equals 0. That's the main thing you need to look for, and as well as the gradient. And for quadratic graphs, you'd have seen them a lot by now. They are U-shaped or N-shaped graphs, or like smiley faces almost. And you'll need to label things like this is a root, these are both roots, this would be literally the turning point. And where it crosses the y-axis is also called the y-intercept. That's when x is 0. Some other graphs you may need to recognize and sketch are the reciprocal graphs, which looks like this. They basically never, like, almost touch the axis. Because, like, you can't have x is equal to 0 or y equal to 0. And for higher tier is the exponential graph. So let's say you'll have something like this. Exponential graphs tend to be, so they'll often cross the point at 0, 1, because anything to the power of 0 is 1. And then they'll start off really low. They'll just shoot up like this. Now, back to algebra again, is where we come back and we try and solve some equations, like quadratic ones of a higher tier. So one method you could do it is by factorizing. So they'd usually give you a nice one you can factorize. And you can only do it when you've set like the factorized brackets equal to 0. So let's say we got these brackets here. Since anything multiplied by 0 equals 0, we have to set each bracket equal to 0. And then we solve each bit. So we get two numbers, x is equal to 4 and x is equal to negative 3 over 2. Now another method you could use is the quadratic formula. So this is usually when it tells you to give your answer to a decimal place, as it's, well, hard or almost impossible to factorize easily. So you'll be given the formula in the sheet, but you need to make sure that you've simplified everything, put everything to one side and set equal to 0. So you'll have in the form like ax squared plus bx plus c, where like a, b, and c are numbers. For example, if we try and tidy all of this up first, we want to put everything onto the left-hand side. So we take x squared from both sides to get rid of this, and take 2x to get rid of this here. From there, and let me just check something. Right, it works. Then we just use the quadratic formula, so we need to identify a, b, and c. So this is the form ax squared, so just a is a number, that's the 3 here, plus bx, so b as a note is minus 5. And this here is c, the number at the end, so c, that's equal to minus 8. So if we put this into the formula, we get x equals negative b, so that's 5, plus or minus square root of b squared, so minus 5 squared minus 4 times a, so times 3 times minus 8, all divided by 2 times 3. Which gets us square root of 121. Oh, that's nice, actually. So our two solutions are 100, root of 121 is 11, so we can either add, which is 16 over 6, that gets us 8 over 3, or really 2 and 2/3, or we can take away, that's 5 minus 11, all divided by 6, minus 6 over 6, this gets negative 1. Now, the hardest bit, which I think for higher tier on paper 3, is simultaneous equations. So based off the advanced information, these questions will contain one linear and one quadratic equation, a bit like this. Usually, you'd try and make two of the variables match. For example, y is already a match, actually, and then just subtract them to eliminate them. This could work, but it may not always. But you also need to be familiar with the substitution methods, and you should be able to work with both, because you may be forced to work with substitution. So, for example, by elimination, we have the two equations here. If we take them away, so we'll label this equation 2, we'll label this equation 1. If we take the second minus the first, take them away like this, y minus y just gets us 0. X squared take nothing is just x squared. 4x take away x is just 3x. And then negative 1 take negative 4. So we're adding 4 actually. That gets us plus 3. Now what we get is we can use the quadratic formula. So x is equal to right, we're running into a problem again. Right, problem is if we do the quadratic formula, we have b squared, which is 3 squared minus 4 times 1 times 3 over 2. Now, problem is this little square root is 9 minus 12, which is square root of minus 3, which, well, doesn't exist. It's an imaginary number, so this really has no solutions. And this won't work either if we do substitution, either, where we set the equations equal to each other. So we substituted, for example, y equals x minus 4. So wherever we see y, we write x minus 4 in this equation. So we write this here, for example, then solve for x, then substitute your values of x into the either equation again, and then you get your two pairs of values. Now, next are sequences, which are arithmetic ones for both tiers. So these sequences will increase or decrease the same amount. For example, this one will decrease by 3 all the time, from term to term. So try and find the nth term of the sequence above. So the value it changes by, that's your n. So nth term starts off at 3n, negative 3n. Now we need to correct this almost, so if let's say n equals 1, so first term is negative 3, and we need that to be positive 22 instead. So to correct that, we have to add 25. So if we added 25 to this, we get 22. Now, use the answer we've got, which is 3n minus 3n plus 25, to find the 50th term. So that means we substitute n equals 50. So the 50th term is equal to minus 3 times 50 plus 25, which is negative 125. And then if to check if negative 80 is in the sequence. So what we'd do is we'd set up with a little equation. So we'd have minus 3n plus 25 equals minus 80. So what we're trying to do is to solve for n, as in what position is it when n, or the something term, is negative 80. So if we try and solve this, n is 35. So the 35th term is minus 80, from what we can see here. Next, for both tiers still are geometric sequences. So this is where the number is multiplied or divided by the same number from term to term. So let's say we have this little sequence here, and we want to find the next 3 terms in the sequence. So we can already see a pattern. Each number is multiplied by 4 from the last. So if we get the next term, that's going to be 48 times 4, which is 192. Then we multiply that by 4 again to get the next term, 768. Multiply that by 4 again to get the final term, 3072. So we've basically continued the trend, multiplying by 4 each time. Now, for higher tier, geometric sequences might involve surds. So let's say we've got a sequence that starts with the square root of 3 and multiplies by the root of 2 every term. So that's here. Now generate the next 5 terms of the sequence and give your surds in the simplest form. So if the next sequence is root 3 times root 2, which is root 6, then to get the next term, it's root 6 times root 2. This is root 12, but this can be simplified to root 4 root 3, which is 2 root 3. Then it's multiplied again by root 2, so 2 root 6. Then lastly, it's 2 root 6 times root 2, which is 2 root 12, but you can see the root 12 needs to be simplified. So that's 2 times the 2 lots of root 3, which is 4 root 3. So those are the first 5 terms, for example. Now we've got compound shapes for both tiers. Now, any combination of shapes may come up, so you could be asked for the perimeter or area of the whole shape. So there will often be shared sides. For example, find the area and perimeter of this shape. So we've got a rectangle with a length of 16 centimeters and a width of 10 centimeters, and we've got 2 semicircles right here that fit onto the edge of the length, or the width actually. So if we divide this by 2 so that we assume that the circles are equal, they'll have a diameter of 5 each. So first, the area is easy to find. So simply put, that would be the rectangle plus the 2 semicircles. Or really, 2 semicircles make up 1 full circle. So what we do first to calculate the area of the rectangle is this length times the width, so 16 times the width, which is 10. And then the 2 semicircles, or 1 full circle, so the diameter is 5. So the radius is 2.5, so that'll be pi times 2.5 squared. So in this case, we'll have 160 plus 2.5 squared, which is 6.25 pi. So that's our area. For the perimeter, however, we have this length here, the width here, another length, and then we have the two semicircle arcs, or just a full circumference. So the area of a circumference is pi times the diameter, so the total perimeter. So that you have your length, which is 16, plus the width here, which is 10, and then another length, 16. Then you have your two semicircle arcs, which actually make a full circle or a full circumference. That'll be pi times the diameter plus 5 pi. This gets us finally 42 plus 5 pi. Next are cylinders. So let's say we sketch out the cylinder and label its faces. So we'll try and draw its net. So a normal cylinder will look like this. The circle on top, when you extend it down, and it's a circular bit on the bottom. So if we unraveled it, what you'd find is a circle, then a really long, big rectangle that would have wrapped around that circle, and then just another circle at the side. So if we use this net to find, let's say, the surface area and volume, what we can say is first that we know the radius, we also know the height, and we know what pi is anyway. So what we know is that this length wrapped around the circle. So this length here is pi r squared. And then this extended down, this was the height. And then you've got here just your two circles, pi r squared here. So for the surface area, you have your two circles plus the rectangle. So the two circles are just two lots of pi r squared. And then the rectangle, so which is one length is pi r squared because it wraps around the circle. And that's multiplied by the width, which is the height. So in the end, for the surface area, you get 2 pi r squared plus pi r squared h. And for the volume, to understand it, so you have, it's like a prism almost. So the prism is like its cross section, which is the circle times its length. To put it simply, that is just, wait, correction, the length that wraps around the circle is 2 pi r. So the circle area is pi r squared times the length, which is the height, so the area is just pi r squared h. Now, an example, let's say for higher tier, let's say a cylinder's height is 2 times larger than its diameter. The volume of this cylinder is 54 pi. Calculate the height of the cylinder. So we're not given any units, so we don't need to worry much about them. So the height is 2 times larger than the diameter, and we know that the diameter is equal to 2 times the radius. Then that means the height is 2 times 2 lots of the radius. That means height is 4 lots of the radius. So if we start to calculate the volume of the cylinder, so we have pi r squared h equals 54 pi. We can cancel the pi's out first. And we actually want to find the height. So we want the height on its own. And what we can substitute in, we can substitute r out. So we have r on its own like this. And we substitute this in. So when we see r, we just write h over 4 instead. Then we can just get h cubed over 16 equals 54. So we get h cubed 864 since we multiply both sides by 16. H in the end, if we cube root both sides, is just 9.52. Just units. There's no units. Now, next is some trigonometry. So let's say we've got some right angled triangles again. Formula triangles, you can use them if you want. So just remember, the middle bit goes at the top. Now, let's say we've got this here, and we want to find the length of the side labeled x, and we want to give that to 1 decimal place. So what we'd first do is we'd try and find this side here. So that we'd calculate that by, so we've got the angle here, the right angle here as well. So this would be the adjacent side. This would be the opposite side because it's opposite the angle. So we need to use tan. Tan of the angle is O over A. So we want to find O. So O is equal to A times tan of the angle. So that means that's equal to A, which is 8 centimeters times tan of 40. This gets us 6.71 to 79. We'll just write a few decimal places so we don't lose accuracy on early in the question. Okay, so great. So we know that length here. Now we can use this along with this here and this angle. So we've got this angle and we look at it again. So we're only interested in this angle here. So this side we figured out was the opposite. The side labeled x is the hypotenuse, and we've got the angle. So we need sine. So sine of the angle is equal to the opposite divided by the hypotenuse. We want to find the hypotenuse. So if you rearrange this, the hypotenuse is equal to O divided by the sine of the angle. So the hypotenuse is the value we figured out, which is the opposite. So the 6.7129 divided by the sine of the angle, so sine 65. This gets us 7.41. And I've put that to 2 decimal places. Now, you'll need to know about vectors as well. So coordinates can be written like this. So your first number is your x coordinate, the second number is your y coordinate. They can also be written vertically like vectors. So you'd have brackets around these big ones. Now, these points or coordinates can be moved by vectors. So these are called transformations. And they're described usually by that direction. For example, 5 squares to the right, and then 2 squares down. That means they can also be written by vectors, like in the vertical form. So let's say a point goes through 2 transformations represented with the vectors 4 and -3 and -2 and 4. So calculate the vector for the overall transformation. So what we do is we just add the vectors together. And what we get is just 2. So these two numbers are added together, and these two added numbers are added together. Is that in the end? Simple. Next is mainly targeted at foundation tier. So this is symmetry. So symmetry can be looked at in many different ways. For example, via a line. So that's a line of symmetry. So the shape is identical when flipped over the line. If you folded, let's say, the shape along this line, it would match up exactly on either half. So many shapes would have a line of symmetry down the center. Now, another way you could look at symmetry is rotation. So this is the number of times the shape looks the same when compared to the start, within one full rotation. For example, if you had a square and you rotated it, it would look the same 4 times when you completed one full turn, one full 360-degree turn. Now, to look at lines of symmetry, it can be hard at first, but it can be made easier by doing a few things. For example, you could use tracing paper, which you can get in the exam. For lines, you would trace the shape onto the paper and see if you can fold the shape where the lines meet up. For example, folding a square down the center in half. And once you've done that, as many folds as you can, count the number of lines or creases going through the shape. That's the number of lines of symmetry you've made. Now for rotate, for example, with a square, you'd expect one down the middle, another across like this, and another 2 going diagonally. So that's 4 lines of symmetry. Another way you could do this is through rotating the shape. So you first, again, trace the shape onto the paper, place a dot in one of the corners, or maybe in the center of the shape, and then you start to rotate it around slowly, and then check if it matches the original shape once you've rotated it a full time. Again, for example, if we used a square, you'd trace this on, you'd put the dot in the corner, and basically you'll rotate the shape round until the dot has reached the original corner again, and you just record how many times it looks the same compared to the start, ignoring the dot, obviously. Next, targeted for higher tier is the sine and cosine rule. So these are used when you don't have a right-angled triangle. So before the formulas make sense, you need to be able to label each side like this. So angles are always represented by capitals, sides are represented with lowercase letters, for example. And then you should know that angles and sides with the same letter are opposite each other. For example, side A, lowercase a, is opposite angle A. Side B is opposite angle B, and then side C is opposite angle C. Now that you know how to label a triangle, you'll need to be familiar with the formulas. For example, the sine rule, it's this. So the formula still works the opposite way around. You could put it the other way around. Let's say A over sine A is equal to B over sine B. Because really what you want to find, let's say the angle or the length on top of each fraction. If you want to find the angle, use this one. If you want to find the length, use this one. And remember, if you're finding the angle, don't forget to use that sine minus 1 function at the end to get the actual angle. Now, for the cosine rule, to find the length, you'd use this formula, which will still be given on your formula sheets. And don't forget this square, pesky square at the right here. So that means you don't forget to square root. And if you rearrange this whole formula, you could try and find the angle A by using this. And again, since you find the angle, don't forget to use the inverse function. In this case, cosine minus 1. One of the last few topics on geometry for higher tier is bearings. So rules for writing bearings are that they're always written in 3 figures. They're measured in a clockwise direction, so starting from the north line, and then you rotate clockwise, like a protractor, to the line you're going in a direction. For example, if I sketch out the bearing 080, I have my north line, and then I rotate just in a way until I reach about 80 degrees, which is about here, something. That angle formed here is about 80 degrees, and that bearing is 080. Now, you could be asked to draw bearings yourself from scaled diagrams, or you could be told to find unknown bearings by using, let's say, some angle rules. And these link into your parallel line rules, like the co-interior angles and the alternating angles, and angles on a straight line or point. The first two are the most useful. Take a screenshot now. Now we move on to some statistics. So let's say for both tiers we've got two-way tables. Now, first we want to complete the table above, and for foundation, try and represent this in a frequency tree, which is similar to tree diagrams. So we've got the grand total here. These 3 items add up to this. So we take 80 minus 58 minus 10. This gets us 12 stakes that were ordered rare. Using this, we know that this and this add up to 12. We could also find out a bit of information here. So 35 rump steaks along with some number of sirloin steaks contributed to a total of 80. So 35 plus something equals 80. So 80 minus 35 means 45 sirloin steaks were ordered. To find this here, 8 plus something plus 4 is 45. So 45 minus 8 minus 4, this gets us 33. So 33 sirloin steaks that were ordered medium rare. And if we complete the table, we have this. Now, if you try and represent this in a frequency, like a frequency tree, we'd have the grand total at the start. Now, we basically split off however we like. For example, I'll split off by the type of steaks. Example, lump. 35 were ordered here. And then 45 sirloin. And then we split off again from each based on how much it was cooked. So the rare, medium rare, and just medium. So we'll branch out again. So the rare, medium rare, then medium. So the steaks that were ordered rare and were rump steaks, that's 4 of them. Medium rare and rump steaks, that was 25. Medium rump steaks, that was 6. And lastly, we've got the sirloin splitting up. So we have the sirloin steaks that were ordered rare, that was 8 of them. Sirloin steaks that were ordered medium rare with 33. Sirloin steaks that were ordered medium for here. So that's like a frequency tree. So it kind of spans out like this, or splits in branches by detail. Next, for both tiers, I think, still are vertical line and bar charts. So bar charts are used for categoric data. So this involves non-numeric data, things like colors, names, or groups of anything. So ideally, a bar graph should have your axis labeled, suitable scale on the y-axis, and then you'll have your bars, which ideally should be straight, and you should have little gaps in between. Now, vertical line charts are similar to bar charts except they use numeric data. So instead, you'll see, for example, the number of drinks cans sold every year. I could plot this onto a little line chart, a vertical line chart. For example, we'll start with 2010, 2011, like this, and you'll just have a scale up here, so number of cans. And you'll just have an X, it'll just go up like this. It will look something like this. Next are tree diagrams. So let's say I have 10 sweets in a bag, which are either red or yellow. So let's say 4 sweets are red. I take one out and eat it, and I take another one out and eat it. So we need to represent this information in the tree diagram. So the probability of 8, a red sweet, so that was 4 sweets are red out of 10 possible ones, so that's 4 out of 10. And the yellow ones, that was 6, the rest are yellow, so 6 out of 10. So we go down the red path. So if we have another red sweet, that's out of 9 sweets, 3 remaining are red because we ate one of them already. And to eat a yellow sweet, there's still 6 yellow sweets out of a total of 9, so 6 over 9. Now if we eat a yellow sweet first, there's still 4 red sweets out of the remaining 9. And to eat another yellow sweet, so there's 9 remaining, and there's 5 yellow sweets remaining, so we ate one of them, so that's 5 over 9. So let's say calculate the probability of eating one of each sweet. So that will be just red then yellow or yellow then red. So when you're multiplying, you need to multiply the probabilities together when you're doing one event after the other. So that would be red and yellow. So that's be 4 over 10 times 6 over 9. And then when you're combining events like this, like an OR, you'll add them together. And then a yellow then red, 6 over 10 times 4 over 9. This eventually gets us 48 over 90, 24 out of 45. Another question would be, as a practice, is eating at least one red sweet. So how many ways is this possible? So you could have 2 red sweets, so one after the other, red and then red. You could also have a red, then a yellow, or a yellow, then a red. And then if we add all these combinations together, we get 60 over 90, which simplifies well to 2/3. For higher tier again are histograms. So these are like bar charts, but these are used for numeric data again, specifically groups data, and this can be with uneven widths. And we use something called frequency density. So this takes into account the width of the class, as in the wider the class, obviously you'll have more people in it that will be recorded. And the formula for frequency density is the frequency in the table. We divide this by the class width. In this case, we'll use some data from a table, and we'll just write the class width, which I'll write as CW, and then the frequency density is FD. So the class width for the marks in this first one is 15. I'll write the rest out. Then we do the frequency divided by the class width. Then what you'd get is you'd have like your y-axis, which is frequency density, and then your x-axis, which is your marks. And then what you'll do is you'll mark out roughly on my diagram the class widths. And then you'll plot the frequency densities as well. We'll get something that looks just like this. So you can see there's uneven widths and they've got the frequency density. So basically the frequency is shown by the area. And ultimate thing for today is box plots. So you'll need to know the median and quartile. So first, these will split a list of ordered data into quarters. So first, you'll find the median. So there'll be 1, 2, 16. So there's 16 numbers. So that will be between the 8th to 9th position. That's the median. So median is here, so that's 38. And then that will split the data into 2 quarters. So this is your lower quarter, but below the median, and the upper quarter is upper like half is above the median. Then you'll take the middle of each half list. So this is your lower quartile, which is 10. And then your upper quartile is here, which is 44.5. So what you then draw for a box plot is your lowest value at one end, then your lower quartile, then your upper new median, then your upper quartile, and then your largest value. And then to complete everything, it should look like this. It's like a little syringe in the middle or a box in the middle, and it just whiskers out to the edges. And the final slide for tonight is line of best fit. So to do with this, so contrary to what I've said perhaps in science, these are literally just lines. So after plotting some data on a line graph or like a graph, you need to draw a line of best fit usually. So this line of best fit should follow the general trend of the data and should have half as many points on each side of the line. And remember to ignore any outliers. So let's say if I have a graph like this with random bits of data like this, which seems to be generally going up. And then you get this weird anomalous result here, and you'd circle it usually, and just ignore it. And then your line of best fit, which I'll do in a different color, should go something like this. So general trend of the data, so that will be increasing in this case, and then there's roughly half as many points on each side of the line, so through the middle of the like splodge of points. And for plotting as well, remember that they have a very tight tolerance, so like a strict tolerance of half a square. So draw crosses with a sharp pencil. Try and avoid dots, because you really can't see much, like you can't see exactly where the center bit is. Now, for example, you could then be asked to make estimations using your line. For example, let's say if this was number of hours you revised, this is the mark. For example, if you were to estimate it, let's say 2 hours, if I revised for 2 hours, let's say a day, what mark would I get? You'd then draw up to the line, your line, and then go off to the side and use a ruler for this. Now, however, if you're asked to estimate outside your data range, for example, the largest, for example, one person revised for, let's say, 4 hours a day, and that was your largest number. You can't estimate, let's say, someone who revised for 5 hours, like more than that, because you don't have data. You don't know what the trend is going to be like beyond your data. So that's actually a common exam question as well. So you can call this extrapolating. So that's estimating outside the data range. If I repeat it again, for example, let's say the most number of hours someone revised was like a survey to be around, let's say, this was, let's say, 3 hours. You can't, let's say, estimate for, let's say, 4 hours, because that's outside your data range and you don't know what the trends are like beyond your data. For example, it may not increase anymore, it may just flatten off or even decrease. Another example could be estimate the weight of a human that is 3 meters tall. Well, we can't tell because we don't know a human that is 3 meters tall, so we can't make a prediction. So that's it for all for tonight. I hope you found this useful, and good luck with whatever paper you're doing tomorrow.